threaded tree. It's a very simple and small topic. You just have to grasp the meaning of it. You will easily follow, and there are no algorithms involved in the topic. It's just a theoretical topic, and you just need to understand what is a threaded tree. And in order to understand the advantage of threaded tree, we have to consider binary tree traversal, a topic which we have already completed long back. You just have to recall that one, and we are going to improve the efficiency of the binary tree traversal by converting a binary tree into a threaded tree. So what was the binary tree traversal? Visiting all the nodes in a tree. That is the objective of a binary tree traversal. That is, given a binary tree, you have to visit each and every node in the tree. And for that, we have seen two categories of algorithms: depth first traversal and breadth first traversal. Under DFS, there are four types: in order, pre-order, and post order. And you know the differences between the three traversals: in order, pre-order, and post order. So I'm not going to that again. So basically, traversal involves the recursion or the stack based implementation. So when you want to implement the traversal through a program, you have to either use recursion or stack. So the that is what makes it less effective, less efficient. So binary tree traversal implementation involves the usage of recursion and stack. If you can eliminate that, that is, if you can implement the traversal without the need of recursion or a stack, that is what is going to be an efficient traversal. So the alternative called a threaded tree facilitates that. I hope you got the purpose of the topic. We are only going to improve the tree traversal by eliminating the recursion, the role of recursion and stack in the traversal. The next question is that why do we need a recursion or stack while we implement binary tree traversal? That will be covered in the next slide. So in a threaded tree, the null pointers are replaced with the pointers to their successor nodes. This point may not make any sense right now, but you will get to understand this point as we proceed, especially if you are going to traverse more frequently. So this is the drawback. It's pointed out that the usage of stack makes it less efficient. But the answer for the purpose of the stack is that this is the second point. The reason we use recursion or stack is that at each step, we cannot access the next node in the sequence directly, and we must use backtracking. I will show you a demo of this to understand better. So basically, backtracking is involved or required in tree traversal, and backtracking is facilitated by the stack. So it is the need of backtracking that brings the need of stack. So if you avoid backtracking, you can also avoid the usage of stack. That will be done with the when you implement it using threaded tree. So we are going to understand the role of stack while we traverse when you do the traversal. So let us take the in-order traversal. As the common traversal is in-order traversal. So what we do with the in-order traversal, we start from the root, we go to the leftmost node, and then we print the or we process that particular node. After that, we process the parent of that node, and then we go towards the right side subtree of that particular node. So this is the typical traversal. We start from root, go all the way to the leftmost child, and then go back to the, remember I'm now referring to the word go back, okay? In other words, backtracking. So after reaching the leftmost child, you have to go back to the root again. That is root, that is parent of that particular node again. Only then you can print it, because in-order traversal is about left, parent and right. So after reaching left, you have to once again backtrack or go back to the parent again. After that, you can go to the right subtree. So it is for that particular purpose a stack is needed. So because the in-order traversal is a depth first traversal, we follow the left pointers to the far left leaf. When we find the far left leaf, we must begin backtracking to the process to process the right subtree. Okay, I think this example will clarify this better. Say for example, I want to perform in-order traversal in this particular tree. Uh, but let me ask a question. So can anyone just tell me the result of this in-order traversal for this binary tree? Just type it in the chat window. What will be the result of the in-order traversal on this binary tree? I'm just looking at your chat window to see the correct answer for the question. What will be the in-order traversal result for this binary tree? Anyone listening? Okay, okay. BCADE. BCADE. Somebody have typed BCDAE. BCDAE. BADAL. BCDAE. Okay. So, okay. Whatever the answer you have provided, now you will come to know which is the correct answer. Uh, so, what happens is that in the case of in-order traversal, the traversal begins with the root, and from the root you have to go to the first left child, and from the first left child you have to go to the last leaf node, which is B, and then it gets printed. So B will be printed. After printing B, you will come back to C and you will print C. It is for this coming back you need the stack. Okay, when you implement this program you will understand this better. Since you don't have the practicals, you may not figure out the role of the stack in the implementation. But if you write the program after reaching B, if you have to come back to C, you should have pushed this into the stack. So that is the role of stack. So you will print B, C, and then D. After D, you will come back to A. So A will be printed, and finally E will be printed. So the actual answer is B, C, D, A, E. Okay. So the purpose is not to teach you in-order traversal, but it is to make you aware of the role of backtracking. So from B, you have to come back to C. Similarly, from D also you have to come back to C. So after reaching D, you will have to come back to C again. From C, you have to come back to A. So for all these backtracking, the stack or the recursion will be required. So we can now understand that we cannot avoid the usage of stack in the current implementation of binary tree. But we can adjust the binary tree slightly to into a threaded tree so that we can avoid the backtracking. So the idea is actually very simple. So what we do is that okay, this is just they are just explaining the process. I have already explained to you. So we are now getting into the solution for the problem, which is implementation of the threaded tree. This leads to the threaded tree concept. When the right subtree pointer is empty, we can use the pointer to point to the successor of the node. That means that if you take this particular tree, uh, see we can the binary tree is typically implemented using double linked list. Okay, let us be clear about it. When I want to implement this binary tree, it will be the double linked list which will be sufficient for this, because only then you can have the pointer to point to left subtree and another pointer to point to the right child. Okay, so double linked list is mandatory, and in the double linked list for this particular node you will have only null pointers because it's not having any child. So the both the pointers will be filled with the null values. Now you can utilize the null pointers by replacing that null pointer by the address of the successor, which is C. So you will put the address of C into the address field of the, or the previous, okay, the right hand side pointer field will be filled with the address of C. Similarly, here also we can fill the address of the pointer with the address of C. As a result, if you reach B, you don't need any stack to go back to C. You can just follow the pointer available here to go back to C. So that is a simple solution which we are calling as threaded tree. I'll show you the threaded implementation of this particular tree. So this was the tree we discussed earlier, which required a stack. Now I'm going to modify this tree like this. So this is the double linked list representation of the same tree. What you see here is that this pointer is supposed to be null. Originally, it's null because there is no right child. But now I have modified it to hold the address of the previous, that is successor. So similarly, here also I have done it. The right child address of the, I mean the right hand pointer of the D is filled with the address of the root. So what happens as a result of this is that I will do the traversal like this. From A I will come to C. From C I will come to B, and I will be printing B. After printing B, I will just use the right pointer to go to C again, go to C. So I don't need any stack. And from C, I will come to D. And after printing D, I will use this pointer to go back to A. So I don't need to go to C again. I'll straight away go to A. This is the idea of a threaded binary tree. Uh, so this is, I'm just repeating because it's very simple, but there is nothing more I need to explain on the topic. So threaded binary tree is just a way to transform a binary tree into a tree which is by replacing the null right pointers. Remember, we are not doing anything with the left pointers. Okay, only the null right pointers are replaced by the address of the successor nodes, so that we can traverse without the usage of any stack. Now I have a small exercise for you. Uh, this is just being explained. I don't need to read out that. So no recursion or stack is needed for traversal. This is the only benefit of threaded tree. So now you may try this particular tree yourself. I just will give you a few minutes. Why don't you try it yourself? Try to build the threaded tree equivalent to this binary tree. I'll show you the result after a few minutes. Those who are interested may take a pen and paper and try it yourself. Sai Prashant, just unmute yourself.
Yes, sir.
Okay, so in other subjects, how much of syllabus is completed for you?
They're nearly 2 units, sir. Two. They are trying to finish 2 units.
Oh, okay. I think we are actually ahead of all other subjects. It's because of
Yes, sir. We are ahead.
okay, okay. It's just because of the portion we have, which comparatively very less.
Okay, sir.
Okay, fine.
Thank you, sir.
Okay, I think I can now show you the correct result. So see, you should expect this kind of a question in the exam. That is the point. So you may be given a binary tree like this, and you should convert this into a threaded tree. And remember that the result of the traversal won't change. Okay, so whether you are performing the traversal on a conventional binary tree or a threaded tree, the in-order traversal will produce the same result. It won't change. But thing is that it will become efficient in the implementation. So you won't see on the screen any difference, but in the implementation, it will be little faster. The execution will become slightly faster. So the result for this tree is just this. So you can see that I have connected the right node, right side of the leaf node with its parent or the successor. Similarly, this is connected. It's you just have to do this like this. You just apply that in order traversal 70, 60, 50, 45. From 45 where you would have to go, you have to go to 50. Make a connection here. From 50 you will come to 55. From 55 where you are supposed to go, or what you are supposed to print, you are supposed to print 60 because 50 is already printed, so you have to print 60 only. Connect them. From 60 you will come to 65. From 65 what needs to be printed next? 70 only, so connect them. Similarly, you come to 80. I mean, from 80 you have to come to 75, and then you have to print 80, so you connect them. That's all. And hereafter you don't need any uh, connection. These red lines are all threads. They are called the threads. Additional connections is just for the purpose of the traversal. Finally, one more point to be added is you can also connect both the left and right side. So though as a standard threaded tree is only connection of the right nodes, we can also make it both